Picture a machine that can read a paragraph, pick up the vibe, and then continue writing as if it got it. That's the experience people have with large language models, and it's why terms like transformer, encoder, and decoder show up everywhere. Under the hood, the basic idea is surprisingly simple. An LLM is trained to predict what comes next in text. It doesn't think in words the way humans do. Instead, it learns patterns from huge amounts of writing, how sentences tend to flow, how facts are commonly phrased, how questions are answered, how code is structured. Once it learns those patterns, it can apply them to new prompts by generating one small piece of text after another. The architecture that made this approach scale is called the transformer. You can imagine it like a very powerful text processing factory. It takes text in, turns it into numbers, reshapes those numbers through many layers of processing, and then turns the result back into text. Encoders and decoders are like two specialized roles inside this world. Encoders are designed to read and build a deep representation of meaning, while decoders are designed to write by predicting the next token step by step. Some systems use both roles together, while many modern LLMs mostly rely on the decoder side. By the end of this video, you should be able to hear the phrase decoder-only transformer and actually visualize what that means, what it sees. Before a model can understand anything, it needs the text converted into a form a neural network can process. The first step is splitting text into small pieces called tokens. Tokens aren't always full words. Sometimes they're parts of words, punctuation, or common fragments. That's not a quirky detail. It's one of the reasons these systems handle rare words in many languages reasonably well. Instead of needing a separate entry for every possible word, the model can build meaning out of smaller pieces. Once the text is tokenized, each token is mapped to a list of numbers known as an embedding. An embedding is best imagined as a point in a high-dimensional meaning space. If two tokens tend to appear in similar contexts, the model learns embeddings that end up closer together in that space. That's why ideas like cat and dog can be related in the model's internal representation, even though the model doesn't store definitions the way a dictionary does. It stores patterns of usage. There's one more catch. Order matters. If you only give a model embeddings, the sentence, "the dog chased the cat," looks like the same bag of tokens as "the cat chased the dog." So transformers also inject information about position. Different models do this in different ways, but the purpose is the same. Each token needs to carry not only what it is, but also where it sits in the sequence. After token meaning and position information are combined, the model finally has a structured numeric sequence it can process. Now we can talk about encoders and decoders in a way that feels intuitive. A good mental shortcut is to think of encoders as optimized readers and decoders as optimized writers. An encoder reads the entire input and produces a richer representation for every token in that input. Richer here means context-aware. The token bank doesn't get treated as a static symbol. It becomes bank as used in this sentence. In a phrase like riverbank, the surrounding words push the representation toward the nature meaning. In bank account, the representation shifts toward finance. Encoders are fantastic when your goal is to understand or compare text, like deciding whether a message is spam, building semantic search, or extracting key information. A decoder, on the other hand, is built around generation. It writes text one step at a time. At each step, it looks at what's already been written, then predicts what should come next. This writing process has a strict rule. The decoder cannot peek into the future. If it could see the words it's supposed to generate later, training would be unfair and the model would learn the wrong habits. So decoders use a mechanism that blocks access to future positions, forcing the model to behave like a real writer moving forward through the sentence. In the classic translation setup, both parts are used together. The encoder reads the source sentence and builds a strong internal summary, while the decoder writes the translated sentence while consulting that summary. But in many modern LLMs, the decoder alone is trained so well that it can handle a wide variety of tasks just by continuing text in the right direction. So what makes transformers special? The short answer is attention. Attention is how the model decides what parts of the context matter most when interpreting a token. Take a sentence like, "Sarah handed the book to Emma because she was leaving." When the model processes she, it needs to connect that word to the right earlier person. This is exactly the kind of dependency attention helps with. The model can look back across the entire context window and weigh which tokens are most relevant to the token it's currently processing. In practice, transformers don't do attention once. They do it in multiple heads, which you can think of as multiple lenses. One lens might focus on grammatical structure, another might track which nouns are being referred to, and another might focus on formatting patterns. The outputs of these heads are combined, giving the model a more nuanced view than any single attention pattern could provide. After attention gathers information, the model applies further processing to each token's representation through a small internal network often described as a feed-forward layer. Attention is the part that mixes information between tokens. The feed-forward part is where each token's mixed representation gets transformed and refined. Then the model repeats this process over and over through many layers. Each layer has stabilizing design choices, things like adding the original signal back in and normalizing values, so the network can grow deep without collapsing into training chaos. The result is a system that can build meaning progressively. Early layers may capture local patterns like short phrases and grammar, while later layers become better at tracking longer dependencies and higher-level structure. When a decoder generates text, it follows a rule that feels obvious in hindsight. It can only use the past to predict the future. This is enforced through causal masking. You can visualize it like a triangular window, where each position in the sequence can look left but not right. The word you're generating now can consult everything before it, but it can't cheat by reading what comes next. During generation, the model runs a loop. You provide a prompt, it computes probabilities for the next token, a token is selected, and that token is appended to the prompt. Then the whole process repeats with the new, slightly longer context. That's why generation often feels slower than reading. It's not producing an entire paragraph in one go. It's making a long chain of tiny decisions, each dependent on all previous decisions. This also explains why context length matters. The model can only pay attention within a limited window. Within that window, it can connect ideas and maintain consistency by referencing earlier parts of the text. Outside the window, it has no direct access, which is why long conversations can drift unless important details are repeated or summarized. A lot of what people call understanding comes from this training setup. The model becomes excellent at predicting what comes next in a huge variety of contexts. To get that right, it implicitly learns grammar, style, common facts, and patterns of reasoning that tend to appear in text. It's not a separate reasoning module, more like a skill that emerges from having to be a great predictor. Once you understand encoders, decoders, and attention, the landscape of model types becomes clearer. There are models that are mostly encoders, models that pair encoders and decoders, and models that are mostly decoders. Encoder-focused models shine when the job is to read and represent text, like building embeddings for semantic search or classifying documents. Encoder-decoder models are a natural fit when you want a structured transformation from one text to another, like translation or summarization, because the encoder can digest the input while the decoder writes an output guided by that digestion. Decoder-only models are what many people mean when they say LLM. They're trained on the simple objective of predicting the next token across enormous amounts of text. That objective sounds narrow, but it turns out to be incredibly flexible. If you phrase a task as, "Here is context, now continue in the correct way," the decoder-only model can do surprising things: answer questions, write code, summarize, translate, or role-play. The model is still doing the same fundamental action, continuation, but the prompt shapes what continuation means. Part of why decoder-only models became dominant is practical. The architecture is straightforward and scales well. Training can be done efficiently on massive datasets, and the same interface works for almost everything. You give it text, it continues text. If you only remember one picture, make it this. Text is split into tokens. Tokens become embeddings, and the transformer repeatedly uses attention to pull the most relevant context into each token's representation. Encoders are best thought of as readers that produce context-aware meaning, while decoders are writers that generate left to right without looking ahead. Modern LLMs often rely on decoder-only transformers because next token prediction scales and adapts to countless tasks through prompting. Once that clicks, the jargon stops being intimidating. You can hear attention head and think one lens focusing on relationships, or hear causal mask and think no peeking ahead. And suddenly the whole system feels like a coherent machine instead of a pile of mysterious terms.